Hi everybody, good evening. I'm Victor Manuel Gonzalez and I come from the Autonomous University of Nuevo León in Mexico. And today I'm here to present you the second part of my thesis research about aeronautical materials. So the title of this poster is the evaluation of mechanical properties of biolaminate of linen fiber reinforced with alumina nanoparticles. So as some of you might not know, but composite materials have a really long history in the aeronautical industry. It has been over 80 years of history. So in the 1937, the first child F-46 contained a fuselage and a structure of components made of laminate wood covered with bakelite. So it was manufactured by pressing, and it was the first commercial aircraft that was manufactured with polymers at that time. And the production system implemented was presented by a lower cost in comparison with some other manufacturing. So it was manufactured by pressing. At that time, they were facing some shortage of steel and materials. Currently, the world's largest manufacturers of aircraft, such as Airbus and Boeing, have some of their aircrafts made of 50% of their components in weight of composites. These composites are mainly composites reinforced with fibers. Fibers like carbon fibers, like glass fibers, and some other fibers like Kevlar fiber. However, glass fibers have some disadvantages, and through the time has been displaced by the aeronautical applications, such they have a really high density. So these fibers are also not very elastic, they are fragile, and they are delicate to use in the manufacturing. Also, they are not biodegradable. Also, we think that flax fibers or linen cloths can take this place, and also for application where we don't need high performance mechanical properties. So we think that mechanical will be a great opportunity for this will be new generation of materials. So in our case, we are using EPOLAM 5015 hardener and monomer. We are also using Biotex Flax fibers, and also we are using alumina nanoparticles with a 50 nanometer size. We prepare our samples for tension testing. In this case, some tabs of 1 inch by 10 inches, and we add some tabs for gripping. In this case, aluminum. Our aluminum tabs were made with a size of 1 inch by 2 inches. We prepare our samples for 10 millimeters thickness. So now we can start with our testing. It was made with a temperature of 24 Celsius degrees, at the speed of 0.08 inch per minute, and initial gauge length of 6 inch. Now for thermogravimetry test, we used, it was made by using aluminum pans. We took samples, solid samples of the material by cutting it from some of our tabs. So we use a 10 Celsius degrees heating rate and an air atmosphere. So now, as a result, in the case of our material without reinforcement, we found that the results of mechanical testing was up to 43 megapascals, and for the reinforced one, will reach out up to 39.9 megapascals. In the case of our material without reinforcement, we found that the arithmetic media was 48 megapascals and 47 megapascals. So in this case, we found a small decrease in performance. So now, moving on the thermogravimetry test, we found a very substantial difference. As you can see in the graphs, we found that the degradation of the materials once we lost humidity of the sample, in the case of the non-reinforced one, was about 260 Celsius degrees. It was keeping about 96%, 96.5% of their weight. And then in the case of the biolaminate with reinforcement of nanoparticles, it was keeping about, or the critical loss of the mass of our sample, it starts about 232 Celsius degrees. It was keeping up to 96.55% of the weight. Now, as a conclusion, The addition of nanofillers does not now any meaningful changes on the mechanical performance with the tension testing. What it means is we don't find any improvement on mechanical properties, but more research is needed to determine if the failure, more research mechanism of the material was affected by the reinforcement. Also, whether mechanical testing is needed to find other possible effects under the different mechanical scenarios like impact testing or flexing testing. Also, the new biocomposite material shows great results in thermal performance. However, a slight improvement was expected for some other biocomposites we have seen in other research. It shows better thermal capabilities, and our gain in our material is a clear increase in performance of 13.8%, and it can be seen as a fantastic opportunity to reinforcement against more thermal demanding application. Thank you very much for being on this talk. I hope you enjoyed it, and let me know if you have some questions. I will be very happy to answer all of them. You can also find me on LinkedIn. And to see you soon. Bye. Have a great day and enjoy the Congress. And